Okay, so we've all been there, right? You run a finite element model, and the results you get back are, well, they're just physically impossible. Today, we're diving into a really cool paper by Pérez-Escudero and his team that tackles this exact stability problem, but in the world of semiconductor modeling. Now, for those of us in the FEM community, we know our tools are powerful. But what happens when they just fail? When they give you answers that make no physical sense? So the standard way to do this uses these drift-diffusion equations. And here's the problem. They're convection-dominated. That means transport effects just swamp the diffusion effects, which, as you know, is a real headache and makes them notoriously unstable, especially on coarse meshes. And the results of that? You get these wild, spurious oscillations. You even get negative carrier densities, which is just nonsense. This forces you to use incredibly fine meshes, which of course is super expensive computationally and often just not practical. But this is where the paper gets really interesting. Their solution is so elegant, it's just a clever change of variables. So instead of trying to solve for the carrier densities directly, the authors solve for their logarithm. It's a simple trick, but it creates these mathematically smoother variables that are just so much easier to work with. So, how does this actually stack up in practice? Well, let's look at the results on a coarse mesh, because the difference is pretty dramatic. And here it is. This just illustrates the payoff perfectly. On the exact same coarse mesh, you can see the standard method is a complete mess. It just fails. But the logarithmic formulation, it's clean, it's stable, and it gives a solution that actually makes physical sense. All right, so the big question then is, what's the most robust combination here? What's the best strategy to use for real-world stuff? And the paper gives us a really clear, actionable takeaway. The logarithmic formulation, when you pair it with a Newton-Raphson solver, that's your most efficient and robust choice for these kinds of simulations. Which really leaves us with a powerful question, doesn't it? Where else could a simple, elegant mathematical fix like this logarithmic change of variables, be the key to cracking numerical instability?